Hello. In this talk, I'm going to talk about the LMD Generic Global Climate Model. It's a project that has been developed by many people from many institutions. I won't have time to sub them all. But let's start with some background. So at LMD, for many years, 30 years maybe, we've been developing climate models for the solar system atmosphere, starting with the Earth. We are lucky to be in an institution that developed a big Earth climate system model, and it's very good for us to have resources, state-of-the-art resources to do climate modeling. And for more than 20 years, we've been adapting such models to the other planets, starting with Mars, Titan, Venus, Pluto, Triton. Recently, we've also been testing the model on giant planets. And on this basis, we've learned a lot. What have we learned? Well, first, we've learned that indeed, if you adapt a model from the Earth to the other planets using the same kind of equation, it works. By many measures, you can really predict very well the behavior of an atmosphere like Mars, like Titan, like Venus. Sometimes it's quite surprising. Of course, nature is sometimes complex. Sometimes the global climate model fails if you miss a physical process, if you don't present it well, especially if you have positive feedbacks or non-linearities. You have a problem also if you have very long time scale that are difficult to represent with a GCM. And of course, if you have a dynamical system that is weakly forced, then the equations must be super good, super well solved to really find the reality. Nevertheless, a third lesson has been that the different climate components, the dynamical core, the binary layer scheme, and so on, can be applied without major change to Mars planet. The equations that has been originally developed for the Earth, they do work on other planets. On this basis, after testing that in the solar system, we've decided that maybe we could try to develop a universal climate model, a generic climate model, to simulate them all, one model to simulate them all. In other words, we've decided to design a model able to simulate every atmosphere with any composition around any star, with any size, and so on. So, of course, that's super ambitious, but that's the goal, that's the spirit. So we've done that for more than 10 years now, and we've applied such a model to many applications. For instance, we've been using the generic Lmdg GCM to model ancient climates to understand geological records, for instance, early Earth, early Mars, ancient Titan. But of course, we've been also been using this model to study exoplanets, to prepare, interpret telescopic measurements, and also to address key scientific questions regarding habitability, to define the habitable zone, understand running greenhouse glaciations, and also to study specific cases like TRAPPIST-1 or Proxima b. So how is designed this generic global climate model? Like every GCM, we have different components that are used, like a dynamical core to compute large-scale atmospheric motion and the transport. And at every grid point of this dynamical core, we have to solve all the physics, the relative transfer, the subgrid scale dynamics like turbulence, the thermal and subsurface thermal balance, the condensation of volatile, the aerosols, so on, so on, so on. So let me give you some details about that. First, let's start with the dynamical core. What do you use in the generic global climate model? Well, we use several dynamical core. Historically, we've been using, for most papers that we have been publishing, the traditional, what we call traditional Lmdg, latitude and longitude, grid point core. So it's very well validated, but of course it has a problem. We have a singularity at the pole that requires a filter to deal with the very high resolution you can reach near the pole. It is parallelized, but it does not scale very well. Beyond the 32 cores, it's not really useful to add more cores, and so we have a limitation in the velocity of this simulation. For several years now, we've been developing in our lab a new generation dynamical core named Dynamico by Thomas Dubos and the team. So it's really much more modern. We use an icosahedral grid, you can see here. It's regular, there is no singularity at the poles anymore. And this one is very well scaled. In other words, we can use it on a massively parallel architecture with more than 10,000 cores. For instance, we've been using it because you can go to very high resolution quite fast to simulate, you can see the grid here, a giant planet like Saturn. So this is coming from a paper by Emmerich Spiga et al. This year. And you can see how well with this high resolution simulation, this includes the physics, radiative transfer, you can simulate the different scale and the cascade of energy from the turbulence to the higher resolution jet. So this is using the generic climate model. I have to add that in addition to the two global dynamical core, we're also using the WRF core to do mesoscale and microscale cloud resolution simulation, and there is a talk by Maxence Lefebvre using this during this workshop. Needless to say that, of course, if you want, you can also you can not use a dynamical core and just use a 1D relative convective model. You have an option in the program, it's very easy. You compute the model in 1D and you have, you can explore very quickly different kind of atmosphere, different heating and so on to use all the advantage of a 1D model super fast. So the question is, can we use such dynamical core classical based on the Earth for any other planets? The answer is yes, in most cases. But sometimes some approximation may not be valid. For instance, on the Earth, we assume that the specific air capacity, Cp, is constant. It's not true everywhere. For instance, Venus is not true. So we solved that, it's included in the model, and this was solved originally for Venus by Sébastien Lebenois. Another assumption that we make is that the air molecular mass is constant everywhere. It's not valid sometimes. For instance, in the Martian polar night, you have CO2 condense and the air molecular mass vary, and this is it induces some density contrast gradient that are not easy to represent and actually not solved in no dynamical core. One approximation that we do often is the thin layer approximation, assuming that the thickness of the atmosphere is very thin compared to the radius of the planet. It's usually true, but in some cases it may not be true. In the case of Titan, for instance, it's interesting, and we've been studying that, but it's not yet available in the GCM. Sometimes some people claim that the hydrostatic approximation is not valid always. I think at global scale it should be, but this can be a debate. And finally, there is one thing which is always neglected on the Earth, is the effect of gravitational tides in the case of a planet very close to its star with an eccentric orbit, or if you are a satellite of a giant planet, Titan, for instance, an example, then you can include the effect of gravitational tides, and we use the equation from Tucano and Nabuero to do that. So let's go now to the other big component that's really specific of a generic global climate model, is the radiative transfer. For this radiative transfer, what we've done is, okay, we use in the GCM two-stream multiple scattering scheme that do the radiative transfer through the gases using the statistical data, using the correlated K distribution technique. So it's not super fast, but it's fast enough for what we do. Once you've said that, the challenge, if you want to simulate all possible atmosphere, is to prepare the correlated K coefficients for any cocktail of gas that you need. So to make that not too difficult, to make that easy, we design a set of tools that start from the Hytron spectroscopic database. You use a tool that we call K-spectrum that allow us to simulate line-by-line spectra for various pressure, temperature, composition, and so on. From these line-by-line spectra, using the tool Make K, or more recently, we have a new tool developed by Jérémy Lecomte named ExoK that enable us to compute the correlated K database for various pressure and temperature. It's a grid. And in the GCM will use this database, this matrix, and interpolate it at the right pressure and temperature it needs. That's the way we work. If you have a gas mixture, then it can be a problem. Of course, you can always, if you have the time, use the full system for the gas, the mixture you want, and you can fully simulate everything. It's time consuming. Gas spectrum is very robust, but very slow. We want to accelerate it, by the way. If you want to go faster, you can start from a pre-computed gas spectra and mix them and do line balance spectra. And if you something smarter and much faster is to go directly from the created K database directly and combine them statistically, assuming that there is no correlation, and to directly compute created K database for mixture of many, many gases. That's the new technique that we're working on right now. So if you have a variable gas, for instance, water vapor, what we usually do is we just add a third dimension in the matrix, the create K database, and we can then account for water vapor. But very soon, we will do it differently. We will use the directly compute online the created K coefficient for the different varying gas from the different created K database using these tricks that I just mentioned. Okay, that's a little complex. Now, even if you have a perfect model to do all that, it will not be easy to compute the rate transfer to any kind of gas you want, because we will always have problem with the spectroscopic database that you can have. When it's very exotic in pressure, in composition, you can have some problem. We don't have the data, notably to compute the continuum and collision-induced absorption when you go to very high temperature and so on. So there is a limitation to this ambition to compute the rate transfer to any kind of gas in any condition. We also do that for different stellar spectra. That means the first we have to prepare a stellar spectra database. You can also set the star brightness temperature. And if you want to do it well, in the GCM, you have to make some modification. In particular, you have to design a supraspectral albedo, notably for the ice, so that depending on the star, you don't have the same albedo that is computed. So I could continue with all the different scheme, the turbulence and convection in the window layer. You can use the same kind of thing that is used on other planets. Surface and subsurface thermal balance. It's about the same thing, although if you have, for instance, a very long year, like on Pluto, you have to take into account that the skin depth will be very deep, and you have to change the different scales that are used in the subsurface model. It's very important, otherwise you can be dead wrong. And finally, something which is very challenging is to compute whatever is related to clouds, the volatile condensation on the surface and in the atmosphere. So very quickly, what we do is we have different kind of quite simplified scheme to compute the large-scale condensation and sedimentation. We usually assume a prescribed mixing ratio for the CCN, and then we condense whatever volatile you want, H2O, CO2, N2. Well, this is just to show you that we can do crazy things. And depending on the amount of condensation, you will change the radius of the particles, and then the precipitation, the sedimentation will be more or less fast, depending on that. If you have a lot of particles, like on the Earth, you can have coalescence, and then you have precipitation, rain if you want. And for that, we use a robust, simple scheme like the one developed by Olivier Boucher in the 90s. On the surface, usually we have what's called a bucket model. You have, it rains, for instance, and if you have too much rain, you have a runoff and the water goes somewhere else and so on. In the Lmdg DCM, something very special we've been developing is a special treatment for the condensation of major components that can induce pressure change. For instance, if you have a CO2 atmosphere and it condenses, then you change the pressure. And if you have, this problem is the same if you have in a very warm condition, if you have water vapor condensing or subliming, then it becomes a major component. It can be a little tricky. And this has been developed and programmed, and for instance, is described in the Leconte et al. Paper some years ago. A big problem is the convection, especially when you have wet convection. So far, we've been using very simple scheme, typically what is called a wet convection, derived by Manabe. but it's probably too simple, and it's time now to develop something more universal based on good physical principle, like a mass flux scheme. And I think there is a talk by Jeremy Lecomte at this workshop. In the other things that we are working on is, for instance, possibly to do more aeronomy. We have an ongoing project to to develop a generic chemistry model. I will not develop that, but if you want, there is a talk by Yassine Jaziri in this workshop. In the future, we could easily extend our GCM into the thermosphere. I'm saying that because we've done it for Mars, Pluto, for Venus. And for that, you need to add some physical processes, molecular diffusion, conduction, and viscosity. That's easy. Non-LT relative transfer, that's challenging. Extreme UV absorption, Joule heating, stuff like that. And Gabriela Gilli is touching this point in her talk during this workshop. Another challenge is to take into account when you have oceans, when you have a lot of volatile. If we have to take that into account, we perform some simulation. At the minimum, you can always put a slab ocean with a high thermal inertia to present quite well the ocean. What is included in our model right now is something which is a little better than that. It's what we call the 2 layers oceanic transport model. It's been published by Francis Caudron in Climate Dynamics in 2011. So it's quite smart. You have at the surface, you have a wind-driven Ekman transport of heat in the upper layer, and you have a return flow at depth. And that transport the heat quite well, present well lots of the things that we can see on the Earth, at least. And below that, you have something which represents the deep transport, which just have a diffusion of heat. And altogether, it works quite well. But of course, in the long term, we will dream of building a generic ocean model. We could derive that from the NEMO ocean model that is being developed in our institute, and Martin Tubé is planning to do such a development in the long-term future. Okay, I'm almost done, but I want to say that there is a remaining problem when you want to simulate a planet. It's a problem that we are working on. The problem is that if you want to simulate a planet on which you have glaciers, lakes, seas, not a global ocean, then you have to decide where to put them. And that's not easy because the fate of volatile, where they will stabilize, usually in cold traps, on the night side, near the poles, where you have a low altitude reservoir, it's not easy to know that. Sometimes it takes thousands or millions of years for the actual water reservoir or any other volatile to stabilize at the location. And the GCM cannot do that. So what we are working on is to develop what we call a planetary evolution model that take into account all the process like hydrology, ground ice evolution, the evolution of glaciers, and so on. And that will run for different timescales from the GCM. For instance, you run the GCM for several years, then for thousands of years, based on the different net fluxes that you get from your GCM simulation, you interpolate what is going on, and then you build a glacier, you make it flow, you make a river flow, and so on. And you continue like that. And you can, that way, imagine that you can simulate the evolution of a planet for millions of years. First, to understand where the volatile, the water, for instance, reservoir will stabilize. But that way, you can also imagine simulating the evolution of the climate due to a change in the obliquity, change the rotation rate, and stuff like that. I'm done. To conclude, I want to say that the LMD generic model is available to all. It's not yet a plug and play online, but we would like to go in that direction. Meanwhile, you can contact us. And coming soon, there will be a reference article on this model. And in fact, we are planning to give a new name for it's not a new name for our different models that we develop, so that it's not only Lmd, but it includes all different teams working on that, and it will be a better name. Thank you very much.